Good morning, myself. I'm Arakshaya. I'm from CSIT branch. My ID is 21955A3301. Today, my AAT Tech Talk subject is image processing, and my topic is Big Universe, Big Data, that is, machine learning and image analysis for astronomy. The definition Introduction to Big Data. The definition of big data is data that contains greater variety arriving in increasing volumes with more velocity. This is also known as 3VS. Put simply, big data is larger, more complex data sets, especially from new data sources. These data sets are so voluminous that traditional data processing software just can't imagine them. But these massive volumes of data can be used to address business problems you wouldn't have been able to tackle before. Today, big data has become capital. Think of some of the world's biggest tech companies. A large part of the value they offer comes from their data, which they are constantly analyzing to produce more efficiency and develop the new products. Machine learning and image analysis for astronomy. Modern astronomy requires big data know how, in particular, highly efficient machine learning and image analysis algorithms. But scalability is not the only challenge. Astronomy applications touch several current machine learning research questions. One of the largest astronomical surveys to date is the Sloan Digital Sky Survey (SDSS). Each night, the SDSS telescope produces 200 gigabytes of data, and to this day, close to a million field images have been acquired, in which more than 200 million galaxies and even more stars have been detected. Upcoming surveys will provide far greater data volumes. Another promising future survey is the Large Synoptic Survey Telescope (LSST), which will deliver wide field images of the sky, exposing galaxies that are too faint to be seen today. The main objective of the LSST is to discover transients, objects that change brightness over timescales of seconds to months. These changes are due to a plethora of reasons, some of which might be regarded as uninteresting, while others will be extremely rare events that can't be missed. The LSST is expected to see millions of transients per night that need to be detected in real time to allow for follow up observations, with a staggering 30 terabytes of images being produced per night. Efficient and accurate detection will be a major challenge. The figure 1 shows how data rates have increased and will continue to increase as new surveys are initiated. The figure shows increasing data volumes of existing and upcoming telescopes. Very large telescope VLT, Sloan Digital Sky Surveys. Very large telescopes are in the time of 1998, that is 10 GB. Sloan Digital Sky Survey SDSS, they are around 2000 a year, which have 200 GB. And Visible and Infrared Telescope for Astronomy VISTA for the year 2009, that is 315 GB. Large Synoptic Survey Telescope LSST in the year 2019 with 30 terabytes, and 30-meter telescope TMT in the year 2022 with 90 terabytes. This is the data rate, that is bytes per night, and the year emerging graph. What do the data look like? Surveys usually make either spectroscopic or photometric observations. Spectroscopy measures the photon count at thousands of wavelength, and the resulting spectrum allows for identifying chemical compositions of the observed objects and thus enables determining many interesting properties. In the second slide, we can see the spectroscopic or photometric observations. Photometry takes images using a large charge coupled device CCD, typically acquired through only a handful of broadband filters, making photometry much less informative than spectroscopy. Although spectroscopy provides measurements of high precision, it has two drawbacks. It isn't as sensitive as photometry, meaning that distant or otherwise faint objects can't be measured, and only a few objects can be captured at the same time, making it more expensive than photometry, which allows for acquiring images of thousands of objects in a single image. The figure shows the first image, increasing data volumes of existing and upcoming telescopes. Photometry can capture objects that might be 10 times fainter than what can be measured with spectroscopy. A faint galaxy is often more distant than a bright one, not just in space but also in time. Discovering faint objects therefore offers the potential of looking further back into a history of the universe. Over timescales of billions of years, thus photometric observations are invaluable to cosmologists as they help in understanding the early universe. Once raw observations have been acquired, a pipeline of algorithms need to extract information from them. Much of image based astronomy currently relies to some extent on visual inspection. A wide range of measurements are still carried out by humans but need to be addressed by automatic image analysis in the light of growing data volumes. Examples include 3D orientation and chirality of galaxies and detection of large scale features such as jets and streams. Challenges in these tasks include image artifacts, spurious effects, and discerning between merging galaxy pairs and galaxies that happen to overlap along the line of sight. Current surveys pipelines often have trouble correctly identifying these types of problems, which then propagate into the databases. A particular challenge is that cosmology relies on scientific analysis of long exposure images. As such, the interest in image analysis techniques for pre-processing and denoising is naturally great. This is particularly important for the detection of faint objects with very low signal to noise ratios. Automatic object detection is vital to any survey pipeline, with reliability and completeness being essential metrics. Completeness of refers to amount of detected objects, whereas reliability measures how many of the detections are actually objects. Maximizing these metrics requires advanced image analysis and machine learning techniques. Large scale data analysis in astronomy. Machine learning methods can uncover the relation between input data, that is, image galaxies, and outputs based on input output samples. And they have already proved successful in various astrophysical contexts. For example, Daniel Matlock and colleagues one used Beisel analysis to find the most distant quasar to date. These extremely bright objects form at the center of large galaxies and are very rare. Passion comparison has helped scientists select a few most likely objects for re-observation from thousands of candidates. In astronomy, distances from Earth to galaxies are measured by their redshifts, but accurate estimations require expensive spectroscopy. Getting accurate redshifts from photometry alone is an essential but unsolved task for which machine learning methods are widely applied. The figure shows an example of two morphology categories. The first one, the spiral galaxy M101. The credit goes to NASA as usual. And the figure 2 describes about Humble Heritage Team, which discovered the ST Cell Association of Universities, Space Telescope Science Institute. Describing the shape of a galaxy. Image analysis doesn't only allow for automatic classification, it can also inspire new ways to look at morphology. For instance, we have examined how well one of the most fundamental features of galaxy evolution, the star formation rate, could be predicted from the shape index, which measures the local structure and not a pixel, going from dark blobs where over valley, saddle point, and ridge like structures to white blobs. It can thus be used as a measure of the local morphology on a per pixel scale. The figure shows the shape index from left to right, the original image of a galaxy merger, the scale-scaped representation of the galaxies, the curvedness, the shape index, finally the shape index weighted by the curvedness. The shape index is defined as an expression. The image shows the attenuate galaxies as seen by the Hubble Scope telescope. Let us look into the big data. While appropriate schemes are valuable alternatives, we're usually interested in an exact nearest neighbor search for astronomical data. In this context, massive parallel devices such as GPUs show great promise. Unfortunately, nearest neighbor search based on spatial data structures can't be parallelized in an obvious way for these devices. To this end, we developed a new tree structure that's more amenable to a massively parallel traverse via GPUs. We can see that in the figure 5. The nearest neighbor searching in the figure A, a buffer KD tree structure depicts an extension of classical KD trees and can be used to efficiently process huge amounts of nearest neighbor queries using GPUs. Conclusion. With this, I conclude that in the field of astronomy, the respective devices take numerous images for a second. This whole images are stored in a big data as information. The data stored in big data is examined by machine learning, where researchers turn to teaching computers to sift through the data, identifying important patterns and connecting that might otherwise be missed. This process is called machine learning and it's an essential aspect of modern astronomy at the center of astrophysics. And the image processing involves a lot of techniques, training to improve analyzing and the properties of the celestial objects or obtaining preliminary inference from the image data. This is how the big data or the big universe is linked with the machine learning and image analysis for astronomy. Thank you.